Hi, so you've already heard our names, but we're here to present the measurements of the double star system, specifically STF 1427, and we used a CCD camera for our pictures. So first of all, we'd like to acknowledge and thank the following people. Jenny Whites for her guidance, support, and motivation through this project and making it possible to conduct this research. Richard Harshaw from Brilliant Sky Observatory for his help and use of his telescope equipment and knowledge. Rachel Freed, VP of INSTAR, for her help with the program ASTROIMAGEJ, and PVCC for giving us the opportunity and space to conduct this research, as well as the reviewers, Robert Buckheim, Richard Harshaw, and Jenny Whites.
Okay, so as far as an introduction, what we were studying was specifically the binary star STF 1427. Now, the reason that it was important for us to take measurements of this binary star was that the study of binary stars allows astronomers to plot an orbit over time. These plotted points add up to an orbital plot, and that allows us to determine respective masses of the stars. By determining respective masses of the 2 or 3 stars involved in these binary orbits, we're able to determine almost all other important information about them. Since stars are essentially the most common cosmic object, and binary stars are the most common stellar system, close study of them yields results that allow us to reveal more things about the universe around us. Specifically, what we were observing was a true binary system that's gravitationally bound. There are 2 different types of binaries: optical binaries that are not gravitationally bound and therefore not worth studying, and true binaries. Now, in observing and measuring true binaries, we take a set of 2 measurements, which is rho and theta. Theta is, we take a central star that is brighter than its companion, and against that, we measure east of true north on the celestial sphere. We measure a position angle in degrees. And then as far as rho is concerned, that is a separation in arc seconds of degrees between the 2 stars. Over time, those change and then give us an orbital plot.
So the yellow-white double star STF 1427 was first observed in 1829 by the astronomer Frederick George Wilhelm von Struve. Struve was able to establish the position angle from the true north at 214.1 degrees and the angle of separation at 9.47 arc seconds. Since his preliminary measurements, there have been a total of 38 measurements that have been added to the Washington Double Star Catalog. And throughout the years, there hasn't been any significant deviation until 1901, when the British astronomer Thomas Espin concluded the system was positioned at 216.76 degrees. This was significant to note because it doesn't reflect the average data. He maintained a relative separation angle of 9.8 arc seconds, so it's most likely his calculations were a bit off. The following years produced results similar to Struve's original summations, the most recent of which being theta, 214 degrees, and rho, 9 arc seconds. This was reported in 2012. Considering the data points have managed to remain close to Struve's original reports, we can most likely assume the star will complete its orbit as it relates to Struve's findings.
So the equipment we used, we did this research project with CCD imaging. So we used the CCD camera at Brilliant Sky Observatory with the help of Richard Harshaw. These observations were done on April 17th, 2018, and we used the Celestron C11 telescope with a CGEM DX mount. Our CCD camera that we used was the ZWO ASI 290mm, and Harshaw used the program the Sky 6.0 to control the telescope and took a total of 10 images over about 10 seconds for us, which we then used to measure our theta and rho.
So in order to make our calculations of the stars, we had to use 2 programs, one of which was called ASTROIMAGEJ, and we were initially having some problems with running and using the program, but eventually we discovered that we had to update it. to version 3.2.1. And once it was all updated, we were able to plate solve 7 out of the 10 images, which was suitable to get reliable data. Using the program was relatively easy when it worked. All we had to do was just click and drag between the stars, and the program would do the heavy lifting and calculate the values for us. So overall, it was very easy to use. It was just a matter of getting it to work that was difficult.
So we used a second program. It was a French astrometry measuring tool / software called Reduc. First we had to compile all the FITS files, then stack them together and crop and align them perfectly so we could get more accurate results. Then you would have to click a certain image, click it 4 times, and you get your theta and rho measurements. But unfortunately the program didn't work so well because, as you can see, there's zeros where rho and theta are, which is not possible. And it's a good method, but it's very complex since it's a more foreign software built by different people.
So these are the results we got from using ASTROIMAGEJ and the 7 successfully plate-solved images. So this compares the last measurement from 2012, the 214 and the 9.03, theta and rho, and compares it to the average measurement that we got this time around, to 13.55 degrees and 9.16 arc seconds. And it has a standard error of mean of about 0.144 degrees and 0.018 arc seconds. So this program is a good method. So when we plate solve the rest of the images and take more measurements, this is the method that we will be continuing with. Because these were numbers that we were expecting to see.
So in our discussion, we talked about how AstroIMAGEJ, the numbers we got from that were conducive to everything that we've been seeing in our research. So all of the numbers are pretty much the same. We were expecting the numbers we were getting, and the data. Not a properly worded sentence, but okay. In the finished paper, we're going to have hopefully 10 of our pictures we took into it as well. We might try and incorporate some of the working part for the Reduc, but probably not because we've been having some issues with that. And then in conclusion, we basically learned what we thought we'd learned, improved upon what future people will continue to improve upon in the future years. And then we also started something that hopefully will continue on semester to semester with a research class that's incorporating us into actual research projects that are broadening our knowledge and our horizons. All right. Thank you. Questions? Yes.
How far away are you?
We're not exactly sure.
What constellation are they in?
Ursa Major. Anything else? We good? Can we go now? Yes, Jenny.
So when you analyze more images and you put this data all together, how will the historic data, how will you use that to compare that with the current data? What conclusions or inferences do you draw?
So it's typically. Oh, yay. Thanks. So hopefully it'll continue with the graph you saw earlier in the history slide to continue to form the ellipse that it'll form. It's only been observed for, 200 years now? Around 200 years now, so it's not super long into it because these binary stars can have super long orbital periods, think of comets or asteroids. Not comets, asteroids. You don't see them again for a really long time. So with this, it might take hundreds of years to actually finish an orbit, but it'll look like an ellipse around one of the stars. The big one. Someone else can get up here and talk.
We plan to publish a probably 5 to 10 page paper in the Journal of Double Star Observations, which is a peer-reviewed journal that accepts many other seminar papers such as ours.